How's it going? All right. Hope you all are doing okay today. Um, Before we get started, are there any questions? Okay. So today we're going to be looking at section 9.2. And this is on estimating a population mean. All right. And so the idea here um, is that we have maybe we have a sample of data, and from this sample of data we have a sample mean x bar. Can we use that to estimate roughly what the population mean is going to be? And the answer is yes. X bar is already an estimate of mu. Okay. And depending on the sample size, which again we prefer to be at least 30, but depending on the sample size, it can be more or less accurate. And there's other considerations it turns out as well, and we'll talk about these as we go through this section. So, first thing we do is that we'll state that x bar, the sample mean, is a point estimate for mu, population mean. And usually in statistics, we'll see that's true for each kind of value. Comparing the sample proportion to the population proportion, comparing the sample standard deviation to the population standard deviation. That's other sections in this chapter. We're just going to focus on this one because the basic concepts here would carry over to the others somewhat. But the idea is that whatever data we get from a sample, at least we can approximate what's going on at the population level, even if we're not exactly sure. Because if our sample size is large enough, it's pretty unlikely we get a bunch of outliers here. So we think we can make a pretty reasonable approximation for what mu is based on that. And that's the goal of this section. Alright. Now, depending on whether or not we know the value of sigma, has a big impact on where we go from here. Uh, Depending on whether we know the value of sigma, which is the population standard deviation, uh, impacts how we proceed. That's another factor that's going to affect how we calculate this estimate. Now, we need to talk about level of confidence. It's one thing that we need to talk about. I should go ahead and discuss that now. And I would like to have a book definition for this, but it may not be the case. Oh, you know what? I bet it's in the excuse me. I bet it's in the previous section. Yeah, here we go. Level of confidence represents the expected percentage of intervals that will contain the, in this case, the sample, the population mean. In general, we might call it the parameter, that will contain the sample or population mean. A little bit off page here. There we go. If a large number of different samples is obtained, okay. Now, ultimately what we're going to do is we're going to create what's called a confidence interval in the section. A confidence interval is basically an interval of values that we think the population mean will be between. So we won't know exactly what the value of mu is, but we predict it'll be between these two values that we call a confidence interval. And the idea is that we want to have a certain level of confidence. That means this is the expected percentage of intervals that will contain the population mean. So, do we want to be 90% confident? Do we want to be 95% confident? Do we want to be 99% confident that the mean is between these two values? So there's different levels of confidence that we can use. But if we want to be 99% confident that mu is going to be between these two values, we're going to get one interval. If we want to be 95% confident that mu is between these two values, we'll get a different interval. And if we only want to be 80% confident, then we might even get a smaller interval than that. So depending on the level of confidence, it'll change the interval that we get as a result. So we could do a survey and say, well, we talked to 50 Midland College students, and what could I say? I'm just drawing a blank. Oh well. We talked to 50 Midland College students, and 35 of them drive their own vehicle to campus to go to class in a normal semester, not this semester. And that establishes a percentage, okay, or a mean, however you want to call it. And then we can say, well, 35 out of 50, that's 70%. Okay, well, what does that tell us from that sample of 50? What can we say about the population overall? Well, if we want to be 95% confident, maybe instead of saying 70%, it's going to be between 65 and 75%. 70 was just our approximation based on our sample, but we have to have a little wiggle room there because it may be a little bit different when you expand to the whole population from just a sample. We figure 70 will be pretty close, but to be confident to be in our result, we might be safer to say that we feel like it's going to be between 65 and 75%. And so that's one way that we can use a confidence interval to make a prediction about the mean. Okay. Now, there's two things that go into creating a confidence interval, and those are having the point estimate, which we already know is x bar, and that will be provided to us, or we'll be given the means to calculate it, but usually it'll just be provided. And then we have what's called the margin of error. Margin of error is based on this level of confidence that we've been talking about. So, creating a confidence interval requires two things. The point estimate, x bar in this case, and the margin of error, which we'll call capital E. Okay. So let's look at this margin of error. And we're going to have to look at it in two cases. One where sigma is known, and a second where sigma is unknown. We'll look at the easier one first, where we actually know what the population standard deviation is. Let me just say that if we don't know the population mean and we do know the population standard deviation, that's pretty weird. So we should not expect this too often, to have this level of population data and not have the other one. So this is the less likely case, but it's also the easier case. So I wanted to do it first. Okay. Here, the margin of error is equal to sigma. Well, first we have this term z alpha over 2 times sigma, and then divided by the square root of n. Now sigma and n, we know what those are. It's our standard deviation, and that's our sample size. But now we introduce this term z alpha over 2. Alpha, I don't know if we've used that one to this point. It's basically the A letter in Greek. So we know what's going on here. Let's focus on the z alpha over 2. Z alpha over 2 is a value that is based on the level of confidence. Now, we will always be given the level of confidence that we will use in these problems. So they'll tell us that we want to create a confidence interval with a 90% level of confidence, or we want to create a confidence interval with 95% level of confidence. That'll be provided to us in the question. And so we'll have that information. We just have to work on creating this z alpha over 2 value. Now, alpha is equal to 1 minus the level of confidence. So if we had, let's say we have 90% level of confidence, we get 1 minus 0.90, which will give us 0.10. Now, we want alpha over 2, so half of 0.10 will give us 0.05. Now what z alpha over 2 is, I'm going to show you this once, but I'm actually just going to give you the values in general, so we don't have to do this process every time we work one of these problems, thank goodness. But I wanted to demonstrate at least how we arrived at this. You make a normal distribution. Alpha over 2 is 0.05. So z alpha over 2 is the z score where the area to the right is 0.05 for 90% confidence. Okay, well that means it's 95% to the left. Or 0.95 to the left. Okay, so 95% to the left. We can use our inverse normal calculation here. So our area to the left is 0.95. We'll use 0 for the mean, 1 for the sigma, because we want a z-score. And calculate, and we get a value of 1.645. Okay. Now again, I'm not going to have you actually calculate these. I've actually given you the z alpha over 2 values for common levels of confidence. So you'll have that provided. But I wanted to show you at least once how those numbers were arrived at. And these are the ones that we'll use most often. We have 90%, 95%, and 99%. So we just found 90%, that's excuse me, 1.645. For 95%, that is 1.96. And for 99%, that's 2.576. And if you look at the formula sheet I had previously uploaded for chapter 7, 8, and 9, those numbers are there. Those are already on the formula sheet, so you'll have that information provided. So what we'll do is, if depending on which level of confidence we're provided in the question, we look up the corresponding value for z alpha over 2, and then use that to plug into this formula. Okay. So that's how we would go forward with that. All right. That's how we calculate the margin of error if sigma is known. Next, we want to look at the margin of error if sigma is unknown. Okay, in this case, our error term E is T alpha over 2 times S divided by the square root of N. You'll remember that S is the sample standard deviation, so as long as we have sample data, we'll be able to find both the sample mean and the sample standard deviation. We've done that previously. Just by putting the numbers into our calculator and getting the results. Now, and we know S and N, those will be given to us. It's really up to us to decide what T alpha over 2 is. This is a little bit different. This is based on the T distribution, which we have not looked at yet, but it's really just another table we have to look up things on. And it uses the value, the level of confidence, and the sample size. specifically, it uses the sample size minus 1. And we call this value degrees of freedom. And I'll shorten that to df, and then degrees of freedom is just equal to n minus 1. So sample size minus 1. And so what a degree of freedom is what it basically is happening here is each data value beyond the first begins to alter the statistics for a sample. And so each data value beyond the first, that would be sample size minus 1. So this is just going to be a table. And let me show you the table that I included in the formula sheet. Now, this is the formula sheet I'm looking at right now, and so this is what we've been talking about. Confidence interval for the mean. Margin of error, if sigma is known, is E equals Z alpha over 2 times sigma divided by square root of n. And if we have one of these confidences, then we know what value to use for Z alpha over 2. This is what I was saying before. Now, margin of error if sigma is unknown, that's what we're looking at right now. Okay, we have our different formula for E, where T alpha over 2 is based on degrees of freedom, df equals n minus 1, and the level of confidence, which we'll use the table on the next page to find. Okay. So here's our table. Now, this table basically puts the let me zoom in. I can't zoom in any further. Let me do that. It puts the alpha values here, 0.01, 0.02, 0.05, 0.10, 0.20. So instead, on the top, I wrote 99% confidence, 98, 95, 90, and 80. I typed that in over the image to just simplify it a little bit, just so we don't have to worry about too much translation of numbers back and forth. So we'll use either the 99, the 95, or the 90% column. And so we go down according to degrees of freedom, and you can see that it goes down quite a bit. And then we go across to the appropriate column based on the level of confidence. So this is a more straightforward table than some of the other ones that we've looked at. Notice the if n is large, which is here defined as anything bigger than 2,000, significantly bigger than 2,000, we basically get the z value for the t value. Anyway, so this table will be included with the test. Actually, if you looked at the practice test that